The development of the fluorescence microscope and fluorescence microscopy to study biological and chemical phenomena was the result of centuries of discovery, research, and researchers' tenacity to defy what is possible. The fluorescence microscope was created as a product of independent discoveries and experiments that culminated in its construction in the early 20th century. In this brief history of fluorescence microscopy, I will discuss how these mostly unrelated experiments came together to build the first fluorescence microscope, and how scientists from the mid-20th century have used and improved upon the first fluorescence microscope. The Spanish botanist Nicolas Menardez made the first recorded observation of fluorescence. In the 16th century, he wrote that the yellow aqueous kidney wood extract had a blue tint when placed in sunlight. In 1833, Sir David Brewster reported several observations of fluorescing objects in solutions, including the red radiation from green chlorophyll, luminescence of quinine solutions, and luminescence of fluorspar, which contains calcium fluoride. However, the term to describe the observation of objects in solutions luminescing and fluorescing had not been developed. In 1852, Sir George Stokes, an Irish physicist and mathematician, noted that when fluorspar was illuminated with blue light, the mineral emitted red light. Stokes called this physical phenomenon fluorescence, after the mineral fluorspar. To observe fluorescence of fluorspar, Stokes used sunlight as his excitation light. The sunlight was then filtered through an aqueous solution of cupric hydroxide containing ammonia to obtain the blue excitation light. The blue light was then focused onto the specimen fluorspar, and the emission light, along with the blue excitation light, was passed through a yellow filter containing an aqueous solution of potassium dichromate to observe the red light. Stokes was also the first to note that the wavelength of the emitted light is longer than the wavelength of the excitation light. Today we know this as Stokes' law, or Stokes' shift. The process of fluorescence was later explained in quantum mechanical terms by Ukrainian physicist Alexander Jablonski in 1935 by constructing what we now refer to as a Jablonski diagram. The diagram describes the fluorescent molecule as sitting in a ground state. Excitation energy, a photon, excites the molecule to a higher energy state. A series of non-radiative internal conversion and vibrational relaxation can happen in these excited states. When the molecule relaxes to the lowest energy level of the excited state, the molecule returns to the ground state. Energy is released as a photon for fluorescence to occur. However, it is noted that non-radiative relaxation may also happen and no fluorescence observed. As scientists were exploring the phenomenon of fluorescence in the 19th century, England and Germany were in a race for microscope objectives with improved resolution. 4 factors contribute to the resolving power of a microscope: magnification, numerical apertures of the objective and condenser, geometric accuracy of the light rays coming together to form the image, and the wavelength of the illumination light. Near the end of the 19th century, the manufacturer Carl Zeiss and Ernst Abbe made optical instruments based on a mathematical and scientific foundation that greatly improved the first 3 factors affecting resolution, including the invention of the apochromatic lens. Based on Ernst Abbe's diffraction limit, d equals lambda 2n sine alpha, where d is the resolvable fraction size, lambda is the wavelength of illuminating light, n is the refractive index of the medium, and alpha is the half angle at which the objective can gather the wavelength of the illuminated object. Wavelength of illuminating light remained as the last variable to be explored. At the start of the 19th century, German physicist Johann Wilhelm Ritter noticed that the decomposition of silver chloride increased when the interacting color of light was at a shorter wavelength, even beyond the visible spectrum, ultraviolet light. And decomposition would decrease at longer wavelength, including infrared. Using the shorter wavelength of light became the focus of August Kohler to construct the UV microscope based on Nabe's diffraction limit. If light of shorter wavelength could be used, then the ability to distinguish two objects from each other would be improved and smaller objects discerned. However, to use ultraviolet light, a few practical considerations needed to be made. The microscope lenses could not be made of glass, as they are not transparent to wavelengths shorter than 380 nanometers. UV lenses had to be designed for use in ultraviolet microscopy. Next, UV light was used to illuminate the object, resulting in the difficult task of focusing the light using visible light to form the final image from UV illumination, often producing out-of-focus images. Last, transillumination was used for UV imaging, potentially exposing the observer to dangerous UV light. In 1904, German physicist August Kohler constructed the first UV absorption microscope, the immediate precursor to the first fluorescence microscope. Kohler's ultraviolet microscope used quartz lenses, a camera as the detector, and the light of a cadmium spark. However, the light source produced very dim images. Kohler was able to first report autofluorescence of tissues using the UV microscope. At first, he reported the fluorescence to be a nuisance because it reduced the specimen's contrast. He later realized the practical applications of this fluorescence when his colleague Henry Friedrich Wilhelm Siedentopf was able to observe the unstayed ultraviolet image of chromatin in the cell nucleus. Improvements to fluorescence microscopy were needed to make this a practical technique for imaging. In 1910, Heinrich Lehmann of the Carl Zeiss Corporation made the first dedicated fluorescence microscope. This fluorescence microscope used a carbon arc lamp and implemented Wood's light source, which used nitrosodimethyl aniline filter to absorb green, yellow, and orange light, and a U-vial glass filter to absorb blue and violet light. This effectively transmitted light of wavelength 280 to 400 nanometers. The microscope also used a bright field quartz condenser, which had the ultraviolet light enter the microscope objective to eliminate the specimen. For the time being, achieving greater resolution outside light microscopy had been accomplished, but the challenge remained in observing specimens that did not autofluoresce. In order to study specimens that did not autofluoresce, fluorescent dyes or fluorophores needed to have improved specificity. In the summer of 1939, Albert Kunz was on vacation in Berlin, but spent mornings watching autopsies with Oberarzt Kurt Apitz at the Charity Krankenhaus. Kunz found himself with many hours in the day brooding and thinking. During this leisure time, he came up with the idea of labeling an antibody with a visible label. He noted that in rheumatic fever, the Aschoff nodule, a lesion characteristic of the fever, had a local hypersensitivity reaction consisting of group A hemolytic streptococcus and circulating antibodies. However, the hypothesis that these antigens and antibodies were localized to the lesion had not been tested. From Kunz's idle summer days in Berlin, the idea of immunofluorescence was conceived. He demonstrated the feasibility of immunofluorescence in 1941 when he fluorescently labeled an anti-pneumococcal antibody injected mice with a great amount of pneumococci and demonstrated inhibition to demonstrate specificity of the fluorescently labeled antibody. Kunz's experiment demonstrated for the first time that fluorophore-labeled antibodies could localize to specific antigens in tissues. Advances in fluorescent dyes, coupled with the advent of immunofluorescence, fluorescent specificity in specimens had been achieved. As we move into the 21st century, the motivation that drove scientists centuries ago to improve resolution persists today. A recent example of increasing the resolution of the fluorescence microscope was demonstrated by Romanian-born German chemist Stefan Hell in a technique called stimulated emission depletion, or STED. In this method, the excitation wavelength is set to 635 nanometers, and fluorescence occurs between 650 to 690 nanometers. After the fluorophores are excited, the STED beam is then applied to the specimen, except for a small area in the center of the beam that has zero intensity to observe fluorescence. The STED beam is redshifted to create a competing pathway against fluorescence that allows for the stimulated emission of the electron from the lowest occupied excited energy state back to the ground state and emits the same wavelength of light as the STED beam. This creates the so-called donut shape characteristic of this technique, in which the STED beam has a high intensity except for a small area in the center, which permits the molecules to fluoresce. This technique has demonstrated the ability to achieve super resolution in fluorescence microscopy down to 10 nanometers in higher resolution. The development of fluorescence microscopy has its history intertwined with the development of microscopy and describing the physical phenomena of fluorescence. These independent advances and discoveries culminated in making the first fluorescence microscope at the start of the 20th century and has proved to be an invaluable technique in cell biology. As we look to the future of fluorescence microscopy, I believe what Otto Heimstedt in 1941 stated about the future of fluorescence microscopy is as relevant today as it was over 100 years ago. If and to what degree fluorescence microscopy will widen the possibilities of microscopic imaging, only the future will show.